this class, let us begin by considering maximum work as well as lost work. When we are considering a process, we would like to know what is the maximum amount of work that can be expected from that process for various reasons. It could be for designing the process, or it could be for maybe evaluating the claims made by others toward the maximum work that is possible from a particular process. In the same vein, we would also like to know the amount of work that is lost. In other words, in comparison to the maximum work or the ideal work, what is the actual work that you are getting out of the system, and in the process how much work is being lost compared to the maximum work. To do that, let us start here. We have already seen that the change in entropy of the system plus the change in entropy of the surroundings is a positive quantity. Let us call that d epsilon way back in equation 1.6. We also said that the entropy of the universe can only increase. That was one of the statements of the second law. Now let us consider these surroundings as a heat sink, as it is called, at a constant temperature T0. This heat sink is a very useful concept. It actually refers to the bodies whose temperatures do not change despite the interactions with the systems that they are in contact with. For example, there are many things that can be considered as sinks or approximated as sinks. Some of them are given here. We can consider the Earth's atmosphere as a sink. It remains at a constant temperature for a certain period of time, or the Earth's surface could also be considered as a suitable sink, especially for biological systems of relevance. Let me also state this, it may not be completely clear right now, but it will become clear maybe after the 5th module or so. The heat sink is also supposed to be in a condition of internal equilibrium with no irreversible changes occurring inside it. Okay, this needs to be stated as one of the conditions of the heat sink. Let me state it again and leave it at that, and let us wait till the 5th chapter, 5th module, to make a little better sense of it. The heat sink is supposed to be at a condition of internal equilibrium with no irreversible changes occurring inside it. Under such conditions, if the system has a heat interaction of dq, a differential q, with its surroundings, which is the heat sink in this case, the entropy change of the surroundings can be written as, remember the second law that we looked at earlier, ds of the surroundings is nothing but minus dq by T0, minus because of the convention, the direction with which this negative is associated. Remember, we are writing this for the surroundings. So minus dq by T0. Let us call this equation 252. Since we have already identified ds surroundings as minus dq by T0, we will drop the subscripts now just for convenience, and ds will as usual correspond to the system. ds system plus ds surroundings, which has been replaced by minus dq by T0, is the same equal to d epsilon. ds minus dq by T0 equals d epsilon. Let us call this equation 253. Remember, the d epsilon is the entropy that is created, and according to the second law, expanding universe and so on, it definitely needs to be positive. Therefore, the dq by T0 needs to be either less than or equal to ds. This directly follows from this equation. We are comparing this and this. this needs to be less than or equal to ds for this to be positive. We will call this equation 254. These are all very generic, coming right from the second law, and this equals ds for a reversible process that is undergone by the system and is less than ds for an irreversible process. Now, let us look at the first law, some very basics again. Equation 1.3, we know that dq, this is for a closed system, dq equals du plus dw. If we substitute the first law of thermodynamics in this equation 253, ds plus minus of dq by T naught equals d epsilon, we are in fact going to substitute for dq, we will get ds plus dq being replaced by du plus dw by T naught plus d epsilon. We have transposed the equation, therefore the negative sign goes away there. Or if we multiply throughout by T naught and then transpose the equation, we will get T naught ds equals du plus dw plus T naught d epsilon, and then grouping the terms appropriately we can write dw equals T naught ds minus du minus T naught d epsilon. We will call this equation 255. Now, note that d epsilon is positive, T naught is of course the temperature that needs to be positive in Kelvin. Therefore, the product of those two terms T naught d epsilon is positive, and thus dw needs to be less than T naught ds. From here this needs to be positive and dw needs to be less than or equal to T naught ds minus du. Du we do not really know what is happening there. We will call that equation 256. Now, if we integrate this expression, let us say between the states of 1 and 2, it is a straightforward integration, integral dw is w, this remains, this inequality remains less than or equal to T naught ds between integrated between 1 and 2 gives you S2 minus S1 minus du integrated between 1 and 2 gives you u2 minus u1. We will call that equation 257. Now, note this equation, this is some quantity and this is some quantity, and the maximum work possible, since w is less than this, the right hand side, less than or equal to the right hand side, the maximum work that is possible is when w equals the right hand side, and therefore the maximum work possible, which happens to be under reversible conditions, if indicated by w max, can be written as T naught S2 minus S1 minus u2 minus u1. Therefore, we have a measure of the maximum work that is available from a process in terms of the state variables of the system. T naught is of course the temperature of the surroundings, S2, S1, U2, U1 all correspond to the state variables of the system. Let us call that equation 258. We started out by saying this, let me complete this part by re-emphasizing this. The maximum work can be used to arrive at limiting conditions, for example the maximum possible work for a closed system, which can in turn be used for quick estimates, to evaluate claims on design, as well as to begin with the design itself. The lost work, as we said, is the difference between the maximum work and the actual work. Therefore, the ideal or the reversible work minus the actual work, The reversible work, we have an expression here T naught ds minus du that we got from earlier. The actual work happens to be T naught ds minus du minus T naught d epsilon. Therefore, these two terms cancel, these two terms cancel. We have an expression for the lost work as T naught times epsilon. This is integrated. After integration, we get work lost equals T naught times epsilon in terms of the sink temperature, the surroundings temperature assumed to be constant, times the entropy that is created. We will call this equation 259. At this juncture, we have looked at many different things so far in this module, and therefore, it will be good to review whatever we have seen so far, especially thermodynamics, lots of relationships, lots of seeming confusions, but actually there is not much. If you look at it another time, things would be a lot clearer. We will do that before we get on to open systems. So, let us start some sort of a review before we go on to the open systems. We began this module to look at additional useful thermodynamic functions. We said that the internal energy U, the entropy S are typically, along with PVT, are typically good enough thermodynamic functions, and in certain cases we said that certain functions would turn out to be more useful, and we went ahead and defined them. The first one was enthalpy, which is defined as internal energy plus the product of P and V. The next was the Helmholtz free energy, which we will use to a certain extent in this course, but in general it is useful. Helmholtz free energy indicated as A is the difference between internal energy and the product of temperature and entropy, and Gibbs free energy, which is G, which is the difference between enthalpy given here and the product of temperature and entropy. These were the three additional functions that we defined, and then we said that any thermodynamic function needs to be given a reference state. The value of the function of the thermodynamic function, either U, S, H, A, G or the others, makes sense only with a reference state being mentioned. At the reference state, we assign a value of 0 to it, and we went through the exercise of thinking about where the temperature is actually assigned a 0 value. If you think about it, it's an assignment of a 0 value at a certain condition where there is no movement of molecules and so on, and we also looked at where the 0 value of pressure is assigned, where we said it is equal to 0 when there are no particles, with complete absence of particles. And the nice thing about thermodynamic manipulations is that one can fix one's own reference state for a particular application, but only with at a certain point, at a certain reference state, the value being 0. Only if that is done will any of the thermodynamic functions make sense. And then we said that reference state does not really matter. We demonstrated that by considering the difference in, say, U, it could have been difference in anything, for a particular process. We said that if U2 is some value and U2 minus U reference is the value that makes sense at state 2, and U1 minus U reference is the value that makes sense at state 1, U2 minus U reference minus of U1 minus U reference get cancelled out, leading to U2 minus U1. Therefore, whatever is chosen as a reference state does not really matter, because we take differences all the time. And then we went and did some exercises, and we also said that the H, A and G were defined for 1 mole, and if there are n moles of a pure substance, then we can either call that as NH, the value of enthalpy as NH, which will be defined as Nu plus P times Nv. P is an intrinsic variable, it does not depend on the number of moles that are available, but we said that a better terminology would be to consider a superscript T for total values when there is more than one mole that is present. Therefore, Ht equals Ut plus Pvt, At equals Ut minus Tst, these are all definitions, and Gibbs free energy total Gt was equal to Ht minus Tst. And then we went on to consider 1 mole of a pure substance, and we also said at this point that whatever we are going to develop in this module, unless otherwise stated, will be for a closed system, okay. And that is where we have stopped right now. We have developed all the necessary fundamentals for a closed system, and therefore, before we went on to open systems, we thought we could do a review. We started by considering a single component system which exists in a single phase. As we all know, phases that are being considered in this course are only 3, either a gas or a liquid or a solid gas, or it is also called vapor. And we said that for processes that involve closed systems which have negligible changes in their potential, kinetic or other forms of energies such as surface energy, electrical energy, magnetic energy, we could write du equals dq minus dw, this is the first law. And if we consider the process to be reversible, we could write the second law as dq reversible equals tds. And if PV work is the only work interaction that is considered at constant pressure, then dw reversible was Pdv. Under such conditions, we could modify the first law as dq equals du equals dq reversible minus dw reversible, and therefore, we could write du equals tds minus Pdv. You could recall that this became one of the most basic equations for a closed system. And we also said that although we considered various things to arrive at this particular point, that is du equals tds minus Pdv, we said that since this equation contains only state variables which depend only on the state of the system and not on the path taken to reach, say, state 2 from state 1, this is valid for anything as long as it is that of a closed system. And to understand that a little better, okay, before I get into that, nevertheless, the equation as a whole, the equation as a whole is applicable for anything. Nevertheless, the interpretation of the individual terms is applicable only for that particular path. For example, in this case, TdS represents heat interaction only for a reversible process, and Pdv represents work interaction only for a reversible process. That does not change. Nevertheless, the difference between the two, which is du, that is applicable in general, whether the path is reversible, irreversible, whether it has kinks in between it or a smooth path, nothing of that sort matters. And to understand that a little better, because this was one of the central concepts that we were going to use repeatedly later, we sought to understand that better by considering a mountainous region in which our interest was the difference between the heights between 2 points, let us say 1 and 2, or states, if you want to call it state 1 and state 2. Our interest was h2, height 2 minus height 1, difference in heights. We said that there could be different paths that can be taken. You could take a path on the road, a nice road, or you could take a hilly road which is not well charted out. You could take a helicopter and land here. Whatever path you take, the difference in heights between these two remains the same, it does not really depend on the path. That is the same thing that happens whenever we have the final equation in terms of state variables, irrespective of the path that is considered. Also, we said that some paths could make it easier for us to compute the difference in values, difference in thermodynamic functions between the two states. For example, it could be considered that in one of these paths, say along the road, nice road, an altimeter is available, therefore you could actually measure the heights at various points, and the difference between 2 and 1 would give you the delta h that is required. That would always happen. Therefore we choose a path, an experimental path if you will, where the altimeter or the means of measuring the variable of interest is available to us, and once we do the measurement and we bring it down to an equation which consists only of state variables, then we can use that equation in general. We also said that there could be other equations for a closed system which would come in useful, and we derived them also. dH equals, let me not go through the derivation but tell you just the final expressions. You can go back to the slides and look at how we derived them. We said that dH equals TdS plus PdV VdP, and dA was minus STT minus PdV, and dG was minus SDT plus VdP. I think we also put it all together somewhere. Yes, yeah, du equals TdS minus PdV, dH equals TdS plus VdP, dA equals minus SDT minus PdV, dG equals minus SDT plus VdP. These are nice equations to remember, 2.5 to 2.8, especially if you have closed book exams as it typically happens in the university exams. If not, you know how to derive them, and therefore you can derive them reasonably quickly, and you do not have to remember these. We also said that if the number of moles is more than 1, the earlier equations were all for 1 mole of a closed system, pure component. If this is the case, then the same equations are valid. This is not very obvious, and therefore you were asked to look at one of your reference books by Kenneth Denby. You could do that, and there the proof would be given as to why the same forms are applicable even for total even for variables, the thermodynamic variables taken for systems with more than 1 mole of the pure substance. Therefore dUT equals T dST, this is a intrinsic variable, therefore it does not need to have any superscript. T dST minus P dVT, similarly P is an intrinsic variable. dHT equals T dST plus Vt dP, dAT equals minus ST dt minus P dVT, and dGT equals minus ST dt plus Vt dP. Okay, so we looked at equations for a closed system consisting of a single mole, equations for a closed system consisting of more than 1 mole but of only 1 pure substance. Then we complicated it a little bit by considering a multi-component system, but we retained the single phase nature of the substance. For example, this was some terminology, N1 was the number of moles of component 1, N2 number of moles of component 2, and so on. Okay, let me give you the example. If it consists, this could be multi-component single phase system, could consist of let us say air, an example could be air which contains water vapor. Say air by itself has many different components in the gaseous phase such as oxygen, nitrogen, carbon dioxide, and so on, and if you add water vapor to it, it also has H2O. So that is a very good example of a multi-component system but which exists in a single phase. For that we looked at what equations would be useful to use. To derive that, we started out with the generic mathematical representation of a function of a variable in terms of its dependent values. We took ut as a function of st, vt and so on and so forth, and we wrote the total differential going by one of the theorems in calculus. Total differential is partial differential, rather dut total differential is dou ut dou st. St is the first variable that is taken here, with all other variables remaining constant, vt, n1, n2, n3, the constancy of which is represented as ni here, dou ut dou st dst, plus the second variable dou ut dou vt with all other variables remaining constant times dvt, and dou ut dou n1 with all other variables remaining constant dn1 plus dou ut dou n2 dn2 and so on. We have combined all the n terms into this summation sign for compact notation into as sum of dou ut dou ni at constant vt st nj, which represents the constancy of all n's except the n that is considered for the differentiation here, dni. And then we got down to dou ut dou st at constant vt dou ni equals t, and dou ut dou vt constant st ni equals minus p. And we said that then we went ahead and defined one of the fundamental intrinsic properties which will pretty much form the backbone of this course, as you will find out in the later modules. We said that dou ut dou ni at constant vt st and nj equals the chemical potential, and therefore you could write the equation as dut equals t dst minus p dvt plus sum over mu I dni's, and we could derive the other equations also. dgt equals minus st dt plus vt dp plus sum over all I mu I dni, and since we had used the same term here, mu I, whether we started from gt or ut, we had to prove that they were the same. And before that, one of the important points to note is that dou gt dou ni at constant Tp nj equals mu I, this definition is predominantly used essentially because look at the terms that are held constant here, Tp nj, these all are easy to manipulate from an experimental point of view, and therefore this is pretty much a preferred definition of mu I, although you could define it by the other three means also. And this is how we went about proving that the mu I is the same whether you consider whether we started from ut or whether we started from gt. I will not go through the proof, you could go back to your notes and see how we proved it. And this is important, although the chemical potential mu I was introduced in the context of a multi-component system, it is an intrinsic thermodynamic property, thus it is an equally valid concept for a pure component also. And we extended the derivation to other thermodynamic variables of interest such as At and Ht, you could do that, and we have a comprehensive set of equations that are valid for a closed system consisting of multiple components but in one phase. Okay, dut equals t dst minus p dvt plus summation of mu I dni, dgt equals minus st dt plus vt dp plus summation of mu I dni, dht equals t dst plus vt dp plus summation of mu I dni, dat equals minus st dt minus p dvt plus sum of mu I dni. So, irrespective of how the mu I is defined, they are all the same. Now we did a nice exercise by which we could compare the equations with the standard expansions written in terms of partial derivatives, and therefore we could assign some partial derivatives to the thermodynamic functions. For example, we said that this is nothing but dou ut dou st at constant Vt Ni going by a standard expansion for the total differential, which is nothing but T, and therefore this T is also dou ht dou st at constant P Ni, and similarly dou ut dou Vt at constant St Ni was P, and this P is dou At dou Vt at constant T Ni minus St here in terms of an expansion dou At dou T at constant Vt Ni, here it is dou Gt dou T at constant P Ni, Vt was dou Ht dou P at constant St Ni, and Vt was dou Gt dou P at constant T Ni, and this is quite straightforward. We have already seen this. Mu I here was dou ut dou Ni at constant Vt St Nj, here it was dou Ht dou Ni at constant St P Nj, here it is dou At dou Ni at constant T Vt Nj, there is to be a superscript here, and dou here it was dou Gt dou Ni at constant Tp and all other Nj's. So this is a nice relationship between thermodynamic properties and derivatives, which will come out to be, which will turn out to be useful in many manipulations. This is just listing it out. I don't think I will go through it again, we have already seen it. Okay. Then we looked at one of the central equations in thermodynamics, in classical thermodynamics, called the Gibbs-Duhem equation. We went ahead and derived it by starting with the expression for dg and integrating it to arrive at, for the integration we considered a system being made larger and so on and so forth, and we arrived at this equation 223C minus St dt plus Vt dp minus sum of Ni d mu I equals 0. Here note that this gives you the variation with temperature, pressure and chemical potential, the three major intrinsic quantities of a system, and this is called the Gibbs-Duhem equation. We also said this will have relevance later because the temperature gradient would form the driving force for energy transport as heat, the pressure differential would form one of the driving forces for bulk flow, and chemical potential gradient would form be the driving force for mass flow, and so this has some special relevance, the Gibbs-Duhem equation. This relationship between simultaneous variations in the intrinsic parameters T, P and mu I, it is worth re-emphasizing this. Then we looked at Maxwell's relations by applying a very simple theorem, or I should say a basic theorem in mathematics called the reciprocity relationship, which is nothing but if we are considering exact differentials, all our thermodynamic variables can be written as exact differentials, and if it is a function of, let us say, x1, x2 and so on till xk, then df can be written as by a standard means dou f by dou x1 xj dx1 plus dou f dou x2 at constant xj dx2 and so on till dou f dou xk at constant xj dxk, and if we, let us say, if each one of these are replaced by y's, say this one becomes y1, this one becomes y2 and so on, then the reciprocity relationship says that dou yi by dou xn, y could be anything here, x could be anything here, and xj with all other x's remaining constant equals dou yn dou xi at all other xj's remaining constant. If we apply this theorem to our expansions of differentials of thermodynamic functions u, h, a and g, then we got dou t dou Vt at constant St Ni equals minus dou P dou St at constant Vt Ni, dou St dou P at constant T Ni equals dou Vt dou T at constant P Ni, dou T dou P at constant S Ni equals dou Vt dou St at constant P Ni, and dou St dou Vt at constant T Ni equals dou P dou T at constant Vt Ni, and there were probably a couple of others. Yes, yeah, these two were interesting. Dou mu I dou T at constant P Ni equals minus dou St dou Ni at constant T P N J. Similarly, this was by comparison of this, and by comparing this and this, dou mu I dou P T Ni equals dou Vt dou Ni at constant T P Nj. So this gives the variation of chemical potential with temperature, variation of chemical potential with pressure, which could turn out to be very useful. So these were the Maxwell's relations that we considered, and we had written these for a generic case, a general case consisting of, for a pure component consisting of for a multi-component system in a single phase, whereas what is found typically in textbooks initially at least is for a single mole of the pure substance, and for that we could write the first 4 equations directly. Anything relevant to n will drop out, and therefore dou T dou V at constant S equals minus dou P dou S at constant V minus dou S dou P at constant T equals dou V dou T at constant P, dou T dou P at constant S equals dou V dou S at constant P, and dou S dou V at constant T equals dou P dou T at constant V. And then I think we went through some exercises where we saw the use of these equations to solve some useful aspects. Please go through them again, and then we said that we brought in this idea of expressing difficult to measure thermodynamic variables in terms of easy to measure thermodynamic variables. Easy to measure thermodynamic variables were temperature, pressure, volume, either the specific volume or the total volume. Along with that we had added the heat capacity at constant pressure, heat capacity at constant volume, expansivity, compressibility, and we had also said latent heats and heats of reaction, although we did not consider these in great detail in this particular module. Since the values of these are available, if we can express the other thermodynamic variables in terms of these variables, it will be that much easier to evaluate the not so easy to measure thermodynamic variables, and that was demonstrated here. We had defined a heat capacity at constant pressure dou H dou T at P, and either for a pure substance or for any system in terms of T. Similarly, this was specific heat at constant volume dou U dou T at constant V for a pure substance, or the relevant other for any system. And we worked out an exercise by which we could actually express in terms of easy to measure variables quantities such as these, dou H dou T at constant P, dou S dou T at constant P, and so on. The other two variables somewhat easy to measure, for which values are available as tables and figures, as tables at the end of your textbook even. Alpha, expansivity, defined as 1 by V dou V dou T at constant P. Kappa, the compressibility, defined as minus 1 by V dou V dou P at constant T. V in terms of T, V in terms of P, or variation of volume in the molar volume in terms of temperature at constant pressure. This is variation of molar volume in terms of pressure at constant temperature. And we saw an exercise which demonstrated the use of these variables and finding out the not so easy to measure quantities in terms of these variables. We had utilized mathematics and manipulations quite a bit to do this, and then we introduced two useful mathematical manipulations. One was change of variable, where you could express, where data could be available in terms of one set of variables. You would want the same information in terms of another set of variables, therefore you could use a mathematical technique called change of variable to do that. We had given an example in terms of internal energy as a function of temperature and volume, which is typically known, and you want it in terms of temperature and pressure, then you can do this manipulation and estimate the values. Then we considered cyclic transformation, which is very useful, as we saw. Let us go to the final expression. We had derived it, which is the strength of this particular course. We derive everything. This was one cyclic transformation, and we had let me write this down and then point this out. We had this dou u dou t at constant v, dou v dou u at constant t, dou t dou v at constant u equals -1. We said that this follows a cyclic pattern. Whatever is the top goes to the bottom, whatever is at the bottom goes out, and whatever is outside goes to the top. And this can be written for many different thermodynamic variables. The cyclic transformation equals -1, and we also applied that to some sort of a real life situation. Then for ease of use, I had gone ahead and shown you changes in enthalpy and entropy for 1 mole of a closed system in terms of changes in temperature and pressure. This is more of convenience, not really very fundamental, but useful nevertheless. dH was dou h dou t dt plus dou h dou p at constant t dp, and S was also written in terms of temperature and pressure. Then we got these in terms of easy to measure thermodynamic variables. dH equals Cp dt plus B into 1 minus alpha times T dP, and ds we got in terms of Cp by T dt minus alpha V times dP. We worked out a problem. And today we saw what maximum work was and what lost work is. We started out from the very fundamentals, first law and second law and first law in that order, and we derived the expression for maximum work, and we had introduced the concept of something called a heat sink, which is a useful concept which refers to bodies whose temperatures do not change despite the other interactions with the system. And we said that Earth's atmosphere or the Earth's surface is a suitable surroundings for a biological system, which can be considered as a heat sink. And we also said that heat sink, there is internal equilibrium and so on. And we arrived at an expression for maximum work, which was W max equals T naught, the sink or the surroundings temperature times S2 minus S1 minus U2 minus U1, and we said the maximum work can be used to arrive at limiting conditions, the maximum possible work for a closed system for example, or can also be used for quick estimates or to evaluate claims on designs or to start design itself. And then we arrived at an expression for lost work as equal to T naught times the entropy created epsilon. That was a review of whatever we have done in this module and so far we have considered closed systems, and in the next class we will look at open systems.